and sociology, or economics, game theory, and mathematics. So the exact borderline is not very, I mean, you cannot define it. So it's a field of science, fine. But the word artificial obviously means that it's about something that we create. We create computer programs or machines. We create technology that we can use. So it's built by people and it's built for the people. So it's not an independent entity that thinks something alone. These are just technological tools that we can use. Okay, so what AI is not, it's not the science. The field is not about mimicking human cognition or simulating human intelligence processes. I mean, this is more like cognitive science. AI is more about intelligence in general. I mean, intelligence, solving difficult problems that require some sort of intelligence, and it doesn't have to be related to humans at all. Animals are pretty intelligent too. Deep neural networks, another unfortunate term, because, for example, many people in the bigger audience, they seem to think that neural networks are like brain cells. They are not, and they are deep means that they think deep. That is not the meaning. I'm sure you all know that deep refers to the number of layers in a certain logistic regression structure. So they are not more intelligent than logistic regression, so unfortunately. This means that, I mean, since we are talking about tools and technology that people build for themselves, we don't have to worry about issues like singularity or super intelligence or terminators that will end the humankind. I don't think this is a very realistic scenario. And consciousness is totally, I mean, it's a nice topic, but we don't know what it is and how it emerges. I don't know we can do it by accident. Before we understand what consciousness is, that we don't have to worry about that. That's my personal thinking. So, but this, everybody is talking about AI now, and I was saying that they are not very intelligent. So what is going on? Why do we have so many successful AI applications? So the main reasons, I mean, I did my master's thesis on neural networks back in the 80s, and the techniques are pretty similar. So there has been obviously there has been a lot of algorithmic improvements, especially related to deep neural networks. But the main thing is that we have much more data nowadays than we had in the 80s. And if you have a lot of data, you need a lot of computing power, and that we have too. We have GPUs and so forth. Then lowering the bar, people have realized that we don't need to solve first the kind of the strong AI paradox, that we don't need to build an AI that can write or translate a novel. But we can build an AI that can translate food menus or tweets, and it can make mistakes, but it's still useful. So we have a lot of useful applications that are not as intelligent as humans, but they are still quite useful. And last but not least, there are several easy-to-use software packages that can be used efficiently. So the bottom line is that present-day AI solutions work very well in a small subset of simple domains where you have an abundance of data. If you have a problem that fits these cases, you are lucky, and you will probably find pretty easily an existing off-the-shelf AI solution that you can use. But if your problem is outside of the scope of this, then you need to do something more clever. You need to develop something new, and this is what FCAI is about. We try to extend the scope of AI. We try to go beyond state of the art. So that's in a nutshell what FCAI is. So we are obviously a flagship, and that means that we are several things. We are a community of experts. We are actually quite big. We have actively working in our research programs. We have 60 research groups led by 60 AI professors, but the actual community is even bigger than this. We do have a research agenda that aims at bringing this AI in Finland beyond the state of the art. The more active FKI people, they participate in the agenda, but we always try to support any type of activities related with AI, and bottom-up activities bring up new ideas that we are very eager to see. So as you know, flagships are about impact, and we have recognized these 4 areas of impact as the most important. So scientific impact, obviously. So I said, like, our kind of passion is to take AI as a collection of techniques and methods beyond state of the art, so that we can extend the scope of AI. So that's first. It's for the AI researchers to develop AI further, make it more efficient, make it more easily usable. But then we want to collaborate with other sciences so that we can find new uses for AI techniques and create impact in that way. So that's also scientific impact. Then educational impact is obvious. Economic and societal impact, this is an important for flagships. So this we will also do with our partners from the public and private sector. So I mentioned the research agenda and how we try to extend the scope of AI in FKI. So we have a slogan which is kind of it's a little bit silly, but I will read it anyway. It's real AI for real people in the real world. So by real AI, we mean a couple of things. First of all, we mean realistic AI. We don't need science fiction. We are not too interested in kind of speculating like about singularity or what will or consciousness. It's so far away that it's not very relevant at the moment. On the other hand, real AI means that more intelligence, more real intelligence is needed. So as I said, I mean, deep neural networks make wonders in many domains, but they are relatively simple. Some people might even say that they are kind of idiotic or brute force, that you just they work because you have so much, if you have very huge amount of data available. But I mean, they are still quite useful. So, but it would be nice to have even more intelligent methods. So that's real AI. Real people, autonomous AIs are discussed a lot, but we believe that at some point, any AI system will always face a human at some point. I mean, autonomous cars, there may be humans inside or in the traffic or whatever. I mean, like the humans are always present somewhere. So we need to take this into account. So we are building AIs for the people. So we need to explicitly take into account the fact that the AIs will face humans at some point. So that's what we mean by real people and real world, that we are interested in finding solutions that have impact in the real world, not just fundamental research is great, and that's obviously the basis of anything. But we would like to see how the fundamental research creates impact outside the small circle of the very core AI forums as well. So let's take these methods to real world. So so scientifically, we have recognized how to bring AI forward. We have recognized 4 main areas where AI needs to be improved in our mind. So these areas are data efficiency, trust and ethics, and understandability and interaction. So data efficiency means that, I mean, if you have this abundance of data and a simple task, you are fine with deep neural networks if you can afford the computation and energy cost that that it requires. But in many cases, you don't have this much data, or what happens when AI penetrates all the areas of our society and everybody starts using AIs, and everybody wants to use the kind of the computing facilities for this. This is becoming a global phenomenon that these machine learning techniques, they will start using a significant amount of the energy globally soon. So this is quite interesting. I mean, like at some point, this kind of just using the same hammer for all the problems, we need to have alternative problems that are more efficient. This is one view. The trust and ethics view is very much celebrated in Europe. So we want people to trust AI systems. We want them to kind of follow our ethical guidelines and frameworks. And the third aspect is this human AI aspect, that understandability means here like two ways. We want people to understand what the AI is doing, but we would like to have AIs that understand what the humans need. And this is what the interaction is about. It's very, it's a little bit different, or actually very different task to try to build a system for trying to build an AI that assists, for example, a medical doctor than building a system that replaces a medical doctor. So, okay, I'm running out of time. So we have research programs. They are pretty technical and maybe do not open here. But the main thing is that we have at the center, we have these three bottlenecks challenges that we want to solve. We would like to recognize that there are three items, agents in the world, and there's an AI, and there's always a user, and the user is always in the real world. And then at the end, you will get the slides. There's a random collection of highlights of FCAI. These are not selected for this event, unfortunately, so not all of them are so interesting, but like building a computer that sees the world better is obviously related. Hyperspectral imaging is probably interesting for many people. And this teeth implanting is also a medical imaging application. This is just a random collection from a general set of slides, not tailored for this. You can find more examples at fcai.fi. So I will stop here. Thank you.
Thank you very much, Professor Myllymäki. There is already some comments about the slogan. So the slogan is good. So people like that. And also there is a comment that AI for the people. So very good presentation. Thank you very much. So I think
maybe I should go to politics if people like the slogan.
Yes. So thank you very much. So let's continue. So I think that there is a time for questions later on. So you can use the chat box, or later on we can discuss about that. So we continue the program so that we have a quite nice program still ahead. So Professor Jyrki Saarinen from Photonics flagship program. So please take the floor.
Okay, thank you. I just want to check that you hear me and see me.
Yes, I can hear you, and the presentation probably will.
Yeah, I will shut down my video because that's not a most interesting thing. So I will save some space, and then let me then share my screen. Okay, sorry. Okay, so I hope that you see my screen now.
Yes. Yes, okay, we can
good.
see.
Yeah, so thanks a lot, Juha, for the introduction and invitation. So my name is Jyrki Saarinen. I'm the head of the Institute of Photonics at UEF, and my field is about the photonics applications. And I am also the vice director for the BRAIN, the photonics flagship, with the main responsibility on the impact side. So I will tell you briefly about the kind of basics of photonics, also that we understand jointly what do we mean by photonics, and then I will briefly tell you about our flagship. So what is photonics? So it's quite new word which we have started using. In the past, we used more like the words optics and optoelectronics, but unfortunately, optics was usually kind of people mixed with the eyeglasses and so on. So then we have been trying to kind of, let's say, launch the word photonics. So basically, it means the science and technology of light. So it's all about light. And all about light really means that we generate the light. So we use lamps, we use lasers, we have a sunlight, we have also displays. So you are all looking for a display at the moment which generates light. Then we transmit the light. It transmits either in the free space or in the optical fibers. We modulate somehow the light, so the eyeglasses change the transmission and the shape of the light. And then, of course, we detect and sense the light, for example, in many kind of sensors. So this is all about what we study. It's a branch of physics, but it's still very multidisciplinary. So even in this photonics flagship, we have scientists from physics, but also in electronics, chemistry, biology, and ICT, and so on. So it's really a multidisciplinary topic. And when we are talking about light, we don't only mean the visible light, what we see with our human eye. We also usually cover also the ultraviolet light and also the infrared light, because they behave in a very similar way. And we not we, but also the others claim that, let's say, we are now talking about a century of photons. So in the 19th century, the driving technologies were mechanics, steam engines. Last century about the electronics, and then this century about both the DNA biotechnology, but also the photons, the photonics. And the word is coming really that in electronics, the electron carries the electricity, and the object is now the photon, which carries the light, and that's why we use the word photonics. Photonics is really everywhere. So Risto Linturi has made a lot of studies about the most important 100 technologies which will change our life and this century. And he came up with a conclusion that almost 40% of all this, what is going on around us, are based on photonics. So if we look briefly here, so the microscopes are really the core technology. Without microscopes, there wouldn't be new medicines. There wouldn't be new information in the biology and medical fields. We are using more and more also optics and photonics in the medical care, optical imaging technologies. Lasers are used also even for, let's say, making eye surgery or whatever. In well-being, we are measuring us more and more so, and based on light, because we don't have to let's say, penetrate through the human, let's say, the skin to find out what is happening beneath the human skin. In energy, we save a lot of energy when we have now switched from light bulbs to the LEDs. The fields how we are going to grow food is going to change a lot thanks to the LEDs. Also, let's say, the drones and so on we can use for fertilizing and detecting some let's say nasty things in the fields. We can also create energy thanks to the solar cells. More and more we are really measuring things. So we are measuring the environment and whatever based on lasers, light. in consumer electronics, there are a lot of progress now with the novel type of displays. The camera technology is having also great progress today. Even your mobile phones, you may have several cameras, not just one. These are interesting things. So these are swallowable cameras, which are actually used for detecting any problems in your stomach or digestive channels. So there are two with cameras inside this pill, and you just follow them. Then infrared cameras bring more safety for driving and finding, for example, missing people. Then LiDARs are core technology for self-driving vehicles. There are a lot of interesting things about the gesture recognition for gaming and so on. We will hear more about this artificial and virtual reality, which will really change the interaction between human and computers. We are going to hear more about these different kind of detection measurement systems like hyperspectral imaging, and for example, the internet wouldn't be possible today without light signals and optical fibers. The amount of data and the speed needed to transmit all these videos and so on, we couldn't use any more copper wires. There are very good some material about what is the social impact. So there are some material from the European Organization Photonics 21. In Finland, we made a several survey in Finnish to the Parliament of Finland, and then there are a couple of other new things. So these are available free of charge. There are the links in this material. But anyway, let's say there are a lot of what is going on in photonics for health science, healthcare, food, transportation, environment, circular economy, industry 4.0, smartphones, IT, and so on. So photonics is like we call it, it's a key enabling technology. So there's a lot of, let's say, science where we are really can, let's say, do studying photonics as is, but then most of the impact is really coming when we are applying these in the various fields. This is also a very nice report about the photonics in Finland, which is the brand new publication from December last year, which also gives a very nice kind of, let's say, overview about all the kind of photonics what we have, whether it's an industry, research, or education. In the brain, so it's called Photonics Research and Innovation. We have 4 partners there. The coordinator is Tampere University. Then it's University of Eastern Finland, Aalto University, and VTT, and we are the 4 main research organizations in Finland for photonics, but there are also others. So almost all universities have some, let's say, core areas in photonics. We are doing a lot of, let's say, fundamental research in photonics, so around the materials, around components and structures. And there are many interesting things happening when we are going to the more extreme cases. So extreme cases means that we can now make very small features like a nano features, and the interaction with light with those features brings new phenomena. Also with the new lasers, with the new wavelengths, narrow wavelength bands, and also very short pulses. They also open up very interesting things that how we can apply photonics. But here we also studying some let's say important applications which we are also expanding. But in the first 2 years, we have been focusing on LiDARs, various kind of sensors, and also photovoltaics. So mainly the application areas are environmental, healthcare, safety, security, and energy. And then we have also kind of 5th work package where we have a lot of collaboration from the industry. We are listening what the industry needs, wants, what kind of challenges they have, and then we try to solve that. And at the same time, we also are working on commercializing our own research and either to the existing companies or with the startups. About the structure, so I don't go, so we have 4 or 5 work packages. We have a steering committee maybe to highlight something is that we have a very nice scientific advisory board where we have a high-level scientists from all over the world, from US, Japan, and Europe. But then we have also the stakeholder committee where we have representatives from the ministries, from the technology industries, and also from some companies, also from Business Finland. We are also very proud that, let's say, that besides the brain, we were actually able, because the infrastructure is very important, so there are quite expensive investments for experimental research for how to manufacture various kind of optical structures and materials. So we were very glad that the Academy of Finland also accepted the Finlight, which is let's say part of our brain flagship. So it's now part of this FIRI, the international the national infrastructure roadmap. If we look about, let's say, briefly about, let's say, where we can see the kind of, let's say, overlap or the interest between the photonics and artificial intelligence is, of course, data, because I believe that without data, you cannot make decisions which are needed into artificial intelligence. So there are a lot of, let's say, applications where how you can get data. So in the camera technology, like I already mentioned, there's a lot of progress happening so that you can generate a lot of material and information. Also the LiDARs, hyperspectral imaging, we are going to listen more about that. So that's definitely one interesting area where we can collaborate. Another thing where we are going to hear more is also, of course, for example, the AR/VR environment, so interaction between the human and computers. But then on the other hand, how these are areas where we can help the artificial intelligence. But then, of course, there is also one interesting area, and we are going to hear more about that. Because let's say when we are designing optical components, that's a rather complicated thing. So there are many kind of optical systems. There are more freedom how to make these nowadays, a lot of material choices and so on. Of design programs is not enough. You need kind of, let's say, intelligence, and hopefully in the future you can use more and more about artificial intelligence. And we are going to hear a presentation from our dear colleague Irina Lipsitz also in this seminar. So that's about the brain. So you can find more information from our website. We have also the free of charge newsletter. If you want to follow what is happening, you just have to go to the website and subscribe that. And then we are also on the Twitter and so on. So thanks a lot from my side. And then welcome to the seminar.
Thank you very much, Jyrki. So I think that if there's something questions, so please go ahead. So at least there is some comment that it's very good introduction to photonics and AI. So there is the possibility to join forces. So I definitely too easy to see that the both technologies is valuable for each other. So good introduction about the artificial intelligence flagship and also the artificial intelligence, and also the same to photonics. And next we get the presentation where the both are used. So this is a good example how to use artificial intelligence and photonics together. So Janne Paaso from VTT, so please go ahead, take the screen, and the floor is yours.
Hello and good afternoon, everybody.
Yes, we can hear you.
Share my screen.
Yes, we can see it.
Okay, so you can see it, but let's see what happens. Okay, this happens.
So we can see the not the full mode, but the presentation mode.
Yeah, I know how to fix that, but but there is a problem that this Zoom taskbar is in just there where I should fix it. So let's swap this a little bit, do it in a slightly different way. Okay. Can you now see the full screen?
Yes, perfect.
Yeah, I'm sorry, that's always can be a little bit of a problem, but anyways, so my name is Janne Paasa, and I come from the VT Technical Research Center of Finland, and I'm speaking about the APACY project, which stands for Autonomous Processes Facilitated by Artificial Sensing Intelligence. So we have already in the title of the project the AI and sensing, and the sensing is mostly photonics based in this project. So this is a short introduction to the APACY project, about 10 million euro Business Finland co-innovation project, and the end date is actually at the end of this month. We have as research partners VTT, University of Oulu, and University of Tampere, and then we have several companies, and the big companies are Valmet and Autotech. Actually, it's nowadays Metsä Autotech. And then we have several SME companies. Most of them are related to sensor companies, sensor development. And the big goal of the APACY project is to make autonomous large-scale industrial processes possible. So we are not saying that we are solving everything so that the autonomous processes will be possible after this project, but we are going towards that. And what does it mean? We have sensors here, and as you can see, most of them are photonic sensors like near-infrared, mid-infrared spectroscopy, Raman spectroscopy, and camera-based techniques. And micro and millimeter waves are not exactly photonics, and terahertz is something in between. And then we have soft sensors. But then where the AI comes into play is the intelligence to sensing. So here we have model-based estimation methods, autonomous calibration, and dynamic optimization, and so on and so on. But the big thing also is the applications. We have a lot of applications and the pilots. But unfortunately, due to the COVID situation, the pilots have not realized as much on the real factories or paper mills as we wished. But we could still have some pilots. So we have pilots in the mineral processing industry and in the paper and plastics industry, and also a little bit in the plastic recycling. Okay, but then a little bit about the maybe dull things, the showstoppers in the that are kind of the starting point for the APACY project. So if we speak about measurement data, and that is usually the starting points for any AI method, there is quite a bit of showstoppers if you think about the fully autonomous processes in the process industry. The validity of the data, it's usually that the process operators judge that, and measurement calibration, usually that's quite a bit manual work needed for that. And then you don't measure the process parameters too often, and the operators might use their human senses, vision, audio, feel, even smell or taste on some aspects of the process that you cannot really measure today. And if you have abnormal process conditions, then the process operators need to decide on sampling or measurement campaigns to support process diagnostics. And these have led to the research questions. So how can we replace the operator's sensing actions and laboratory measurements with this kind of measurements? And how to operate the sensing systems in an optimal way to enable optimal control and to guarantee the validity of the data. And the third research question is that how is it possible to learn or adapt to or simulate the validity of data, and identify the need for methods for autonomous calibration. And to answer these questions, they are they are answered in the research project and partly also in the company projects within the APACY consortium. But we decided that the project will be very much concentrating on the use cases in the real paper machines and also in the mineral processing. And this might be a little bit difficult to comprehend this slide, but it tells about the paper machine from the wet end to the dry end, and the different measurements that we have there: dryness, moisture content, temperature, moisture profile, paper quality measurements, and then you have also the actuators here, and then you have web monitoring systems and so on. And these letters here refer to the research questions, or sorry, to the showstoppers, and it shows in which areas of the paper machine we are dealing with in the research projects. And the same for the mineral processing. And here you can see that the research is concentrating on, for example, digital twins, automatic analyzer calibration, online imaging, and characterization of mineral slurries, and so on and so on. So really, we are covering the mineral processing chain in this project quite a bit. And this means that, as we heard, the AI for real world, I think that the APACY project has really been dealing with that, how to get the AI methods to work in the real world. Okay, then about the research project results, very briefly. Replacing the senses of the operators, some examples, and the first is the handheld NIR spectrometer. And the problem here has been that the sample usually needs to be in contact with a typical handheld NIR spectrometer. But with this prototype, which is now ready, you can measure from a distance from 0 to 300 millimeters, and actually even further than that. And the measurement time is about 1 to 2 seconds, and you can measure the full spectrum, or then you can compute the moisture content or whatever content you wish based on the embedded computation in this device. And some other examples, and the problem here has been that the commercial high-performance measurement heads, they might not meet the requirements in many industrial process measurements. And for that, we have developed NIR transmission modules and NIR reflection module and mid-infrared drift module, and everything is the goal here is to provide the modules that would replace the senses of the operators, which is kind of the prerequisite for the data, to get the data and the AI methods. And also Raman spectroscopy, mostly for the mineral processing, and there are several challenges that hinder the application of Raman spectrometers in the process industry, and especially in the mineral processing industry, like the effect of varying particle size and solid content. And we have studied this in the laboratory, and the goal has been here to go to the real process lines, but that has been not possible because of COVID, but let's see, we'll continue still. And then about the intelligent model-based measurements and about the digital twins, which has been a big topic in the APACY project. So we have the process here, and then we have the mirror of the process in the digital world, and which is a functional digital twin, which which means that you update all the time the digital twin with the information of the process, and for that you need a lot of measurements. And that is actually quite challenging to get this digital twin updated all the time. But when you have that, then you can use that in the decision making and the process control and for what if type of analysis. But let's go forward. This is an example of intelligent model-based measurements. So in the paper industry, you usually use some radioactive methods to measure the ash content in the paper. But here we have shown that you can also use a create a soft sensor to measure that the ash content based on basis weight, moisture, and fiber amount measurements. So this is a soft sensor, and here you can see that it actually follows the calculated ash content follows quite nicely the measured ash content. Okay, let's go to the AI things, and I agree with the previous speaker about the challenges, and this is especially important in the process industry, that usually the amount of annotated data is limited and is might be very laborious to obtain. So this is a challenge. And also, of course, industrial sensors need to be robust and reliable. So you need methods to for the instrument to assess the validity of the data and the model and reliability. And the AI research in Apache is concentrating on unsupervised and semi-supervised learning methods in industrial settings, and these would reduce the need for manual annotation. And these have been then applied to several use cases. Let's go into the use cases. So in the flotation process monitoring, this is part of the mirror processing. One of the key parameters of flotation in the flotation process is the bubble size distribution, and we have to develop methods to detect the bubbles and estimate the particle size distribution in the flotation process. And this is an inline measurement, a submersible probe into the flotation process. And then methods for particle size estimation, again for flotation process and grounding circuit optimization. And here we have developed the segmentation methods to monitor simultaneously the size distribution of different particle types. And semi-supervised learning, and this is a combination of using unlabeled data to improve the initial AI method that has been used, for example, particle to detect the particles. And this we have shown that it's possible to have a combination of the supervised methods and unsupervised methods to improve the initial estimate with the that has created with labeled data. And self-diagnostic and self-calibration. And if you have changes in the measurement condition that can affect the reliability of your measurements, and one way is to tackle that is to apply dimension reduction methods to map the structure of the measurement space to the to monitor the changes in the measurement state. And another example, quite different actually, this is more like the unsupervised learning. And here we have shown that in paperboard manufacturing, it's important to see, detect the defects in the product. And for that, there is a way to use completely unsupervised learning to detect the defects. And that is based on an idea of modeling the normal situation, which can contain a little bit also the defects, and then having a model for that, and then the computing difference between the measured data and the model, and then in the difference image you can easily detect the defects. So there's a lot of research here, but to conclude, I think this is the conclusion. So I would like to have a holistic approach for AI and intelligence to measurements starting from so-called measurement intelligence. So before you have the instrument, you design the instrument, you put a lot of intelligence there, so that you really know that you are measuring the right thing with as simple an instrument as possible. And then you go to the instrument level, and you have autonomous sensors here with the functionality of self-awareness and self-calibration, self-diagnostics, and so on. And then you can have also model-based measurements there. And then you go to the next level, to the multi-instrument or unit process level, where you have data fusion, machine learning, active sensing, and so on, which deal with the sensors and the optimal use of the sensors. And then you go to the digital twin level, which is operates on the system or process level. And here the measurement data keeps your digital twin up to date, and then you can use the digital twin, for example, system level measurement data validation, or defect detection, or anomaly detection, or missing data substitution, and so on. And then on the full production line, you have the holistic optimization idea here. And the idea here is that to have so-called autonomous sensors, and to have in the future to develop those sensors, you have to take into account the full chain from this measurement intelligence or measurement development to the sensors and to the data fusion, to digital twins, and even to the holistic optimization. And the interesting thing is that I think there's a potential to use AI methods in all of these levels, starting from this measurement intelligence, how to design a really good optical instrument or sensor. And there's even the concept of a digital twin of a sensor, and that is something that I thought that I would say something about that, but unfortunately I think I don't have time for that. But that would complement the picture here, to have a digital twin of the sensor, and meaning the functional digital twin of the sensor that would simulate the operation of the sensor and the interferences there, and also the light and matter interaction, and so on. And that would fit quite well in this chart. Okay, that was my presentation. Thank you for attention. This is the website of the Apache project, and if you want to hear some more, please throw me an email or go to the Apache website. Thank you. Do you have any questions or comments?
Thank you very much, Janne. So there is at least one question in the chat box. So assessing the reliability of the data, how difficult problem is it for the machine, so AI? So if you can shortly give some comment, and then we need to continue. Yeah,
I would say that it is quite difficult because, well, there are some straightforward ways for that. For example, by using the unsupervised learning methods. But the challenge is that that leads easily to a kind of a circular definition, because if you have a measurement instrument, and then you have the data, and then you have the model, and you try to assess the validity of the data by using that data and some a priori information or whatever, then there is a problem that well, if you cannot really use the same data that was the measurement data, or the data that was used to build the model, to really assess the validity of the data. And that is the reason why I think you need the digital twin, or some kind of a broader perspective where you can do let's say cross-validation, or for example, if you have a digital twin, then you can produce an estimate for each instrument that which kind of result it should produce, and if there's a big difference in those estimates, then you can raise a red flag.
Yes. So thank you very much once more time. So later on we can share the presentation, and we need to continue. So thank you very much, Janne. And we continue about the very interesting presentation about how the AI using the optics design. So Irina Lipsvich, please go ahead. Now we can see not the full mode yet, but also your microphone is closed. Okay, now we can see the presentation. Please unmute your microphone. Okay, now we can hear you. I see you. Go ahead.
Good afternoon, dear colleagues. First of all, I would like to thank organizers for inviting me for such an interesting seminar, the possibility to exchange ideas in such a booming field like artificial intelligence. And I completely agree with Professor Myllymäki, who gave a nice motto for the whole webinar: real AI, real people, and real world. This was great. So I present you application of artificial intelligence in optical design. I don't work. Why artificial is wanted in photonics? Because of rapid development of information technology, it became a big gap between computer technology and the ability of person to work with this technology. Computer speed and ever increasing amount of data make it possible to perceive and display high quality information at the model level. Therefore, the devices and technologies can replace a person at all stages where it is required. So, if in the beginning of creating artificial intelligence, the main question was, can a machine think? Then somebody proposed a brain model to simulate more complex problem, and in addition, make process self-learning. And now artificial intelligence continue to develop rapidly, and a new important question arises: can a machine feel? So we present to your attention ideas of the use of artificial intelligence in photonics, including a narrow but extremely important section of it, the design of optical system. This information-intensive section has all the prerequisites of the application of technologies and as expert system, machine learning, neural networks. This statement is supported by several examples. So this is how we understand basic of artificial intelligence, machine learning, and deep learning. And then artificial intelligence in photonics, we consider 3 photonics projects: expert system, computer-aided design, and databases. It will be realized with the methods of artificial intelligence, such as classification, regression, heuristic search, genetic algorithm, linear programming, and neural networks. To make it work and make it real, we used Python libraries. We just started the projects to use Python libraries, and it was successful. And there will be also presented a real example, which was reported at the ODEF conference in Taiwan recently in June, in the beginning of June. So, three pillars or three ways of optical design are starting point, optimization, and analysis. And here are the keywords which I use for work with these parts. So what are the goals of artificial intelligence in RAN design? First of all, is it accelerate the development process for optical system. Then make balance between performance and constraints. Find best solution, even under boundary condition. Improve productivity of the designers and decrease cost, because our goal not to put our design onto the shelf, but to make it, produce it. And cost is also one of the most important points to use artificial intelligence to optimize the solution. So a model of optical design process is presented in the next slide. You see the client or customer, this product, he orders the product, and designer implements it, makes solution with the help of software, and he uses, in case of artificial intelligence, the problem we put to the expert, and expert's knowledge will help to implement this solution. So we find that it is attractive to use artificial intelligence to create optical optical device at design stage. Two main problems can be solved with artificial intelligence. Firstly, creation of expert system for design of optical system, including the most creative stage. Secondly, the choice of starting point and creating software trained directly in optical system design using machine learning and deep learning technologies. The basic for the application of artificial intelligence in the field of optical design is classification. It brings optical system to one of determined classes, which gives an idea how we can design an optical system, how many components it has depending on technical data, customers' requests. So, expert system. The core problem here is the fact that, except in few simple cases, it's very difficult to find a good starting point. And there are usually many solutions to give to a given task. Different starting point will go to a different local mean. RAN design is hard because it's too many local mean. The difficulty arises because of this geometry of lens design landscape. We take into account the dimensions of the housing, the properties, cost, transmission. So there are many requirements, and there are big disbalance between quantity of requirements and quantity of argument and function. So this is the model of expert system. Here you see customer request, and here the classification, where this is aperture, field of view, focal length, spectral range, quality factor, back focal distance, and position of the aperture stop. These 7 characteristics, they describe the technical requirements for any optical system. And using these 7 characteristics, we have to select starting point here. Then we have analysis of it. And if it is good, we are very lucky and we end the process. Yes. If it is not good, what we do then? Then we create merit function, optimize it. And then again and again, so many times it has to be repeated until we get this result. Yes, and then. So to implement this expert system, we need, of course, optical expert. Then we need information engineer for collection of existing solutions. Then we need knowledge engineer, and then it goes to optical designer, user of expert system. So where we take this starting point usually from? There, we can design them as I described before. We can take them from patent literature, vendors catalog, archives, specialized databases, and analytical recreation. So this is an example of expert system, GEOS, generation of optical schemes. Proposed a heuristic algorithm based on elements with well-known properties to select a starting point. So there are some elements which properties are well known. For example, aplanatic surface or near image surface or concentric surface. Concentric surface is completely free of astigmatism and coma. So if we put only concentric surfaces as a base, a structural scheme of optical design, we get system which will be also free from coma and astigmatism. So in the next slide, there is implementation of this, one of the version, Struct 7, one of the version of this software, which really worked, and students design using the software. And this is speed, field of view, focal length, this is 7 characteristics. And when we get them, when we input into computer, this software gives us structural synthesis, which are elements. First element is here. 2 elements, which is double concentric, then correction element, then basic element, and so on and so forth. Then after we have the structure, we get parametrical synthesis and get the result for input into the software. This was interesting software because it has like, it can fit to any professional optical design software which is in the market. For example, Code 5, Synopsys, Zimox, and so on and so forth. And as we are in the university, we teach students how to design. And why some students are smart, some are not very smart. But if we teach not very smart students, why not teach smart computer how to do design? And then smart students also start teaching smart computer. So it becomes like circle for artificial intelligence. Another problem is I described the problem about using it in optical design, but there are many problems which can be artificial intelligence can also be used. This is presented in this part of presentation, which is called computer-aided design. So there is a block scheme for photonics, computer-aided design. And in green, we show the blocks where we add artificial intelligence. For example, GOS, I already told about it, starting point selection. Then it helps in decision making, analysis and decision making, and then in optimization and modification. No one software is like this is in the market. And we propose to make it, to design it. So Model lens design technique can generate starting point, correct Fourier values, improve tolerance sensitivity, find best blast combination, locate strained elements, generate complete tolerance budget. So we can really design the real optical system using this method. Then, of course, we need database, because there are so many. The optical design is about 300 years old, approximately, and here, I mean. And then it is obvious that we have to use this and put it into one place and make a database which has classification, formalization, select of best option, and at the end, machine and deep learning. So we have to put it into circle. Machine will teach itself how to design, how to select the best option, and so forth. And the future lens design program need to incorporate learning and teaching function. And then it becomes a repository of knowledge as well as a set of tools. And why we use Python library? Because in some kind of field of technology and industry, there are many good things were created, but not of them are used for different applications. So we decided to try to use supervised machine learning using Python library to selection of starting point, to classification. So we took note and we used the random forest classifier for this from Python library. So we selected only 3. You remember I showed you 7 characteristics in our. We select 3, G, W, and F. And then optical system was presented here, and we had 3 classes, low, average, and high. And there are borders where we put this, for example, 2.5 F number, then 20 degrees, and focal length is less than 50 millimeters. So we train the classifier and get the data set, which is described in the slide, and then generated a training sample using completely Python library, and import the necessary model and created the classifier object. Then we generate a training set and train the classifier using this method. And we get that this combination got a class number 8 in our classifier. The J 2.8, 160 degrees, and F 1 millimeter. It got the number 6 in our classification. Then we check the operation, and classifier was not mistaken. Here I also put some references on our publication, which we did connected with this artificial intelligence. And this is a recent publication in the conference. And results presented confirm that supervising machine learning can be used for optical system classification with the help of Python library. And the result is received in a few seconds. And it takes more time for human to do the same. And finally, we propose develop expert system for optical design, create new type of computer-aided design with deep learning techniques, populate databases for starting point and merit function of all possible optical systems, which can predict the appearance of new types of optical systems, such as periodic table of elements of Mendeleev, and use existing methods for AI application in photonics. And what we need for this, a good project with strong international cooperation. Thank you for your attention. For contact, you can use this email. Questions?
Thank you very much. So I think that if there is some questions, so please, so can you see the comment in the chat box?
No, not yet. I have to escape.
Yes. So the first of all, this the using the AI in optics design is very welcome, because this optics design, it seems to be very that kind of hot topic at the moment. So at least in photonics in Finland, so many companies, not only the photonics companies but also general industry, they are looking for the optical design knowledge. So so thank you very much about the presentation. So let's take a short break. So we continue after 5 minutes. So 1:25 in Finnish time. So 5 minutes break, and then we continue the presentation from Arno Solin about AI for imaging. So let's take a 5 minutes break. Thank you.
Да, заходи.
Don't worry, let's wait a couple of minutes more. I'm just putting up my slides.
Yes, sulla näkyy jo esitys. Yes. Okay, I think that now it's time to continue. So we already have a quite interesting the first session. So that background about the AI and the photonics, and then some example how to use photonics and AI, and also of course to the optics design. So the rest of the webinar, we get some practical examples how to AI and photonics are working together. So I put in the chat box about the survey, very short survey, that how this event, how you feel the event, and please go through the survey, and also afterwards I share those emails for you about the presentations. So please put your emails in the survey so that I can share the presentations so afterwards. But now we continue about the topic AI for imaging, and Arno Solin, please go ahead.
Thank you. I hope you can hear me okay.
Yes, we can hear
No
you.
complaints. Great. My name is Arno Solin. I'm an assistant professor in machine learning, which of course is closely related to AI at Aalto University, and I also try to push forward the next generation data efficient deep learning research program within FCAI. I was told that I have like around 10 minutes to present, so I'm trying to be very high level here. And the goal is that then we will have a bit of time to discuss, answer some questions, and so on. And that's why I'm not going into the detailed things. I'm just like looking at the big picture here. So the FCAI research program on next generation data efficient deep learning. Of course, these terms go quite well with what Petri said earlier in the previous session. So I'm not like repeating what he said. I think he put it very well there. But the research program itself brings together like top researchers in the field of AI who tries to develop new methodology, new methods, and also to apply these methods to various types of domains of applications. And of course, for deep learning, that kind of goes well with imaging or photonics in general. Often deep learning is kind of the propelling methodology for computer vision or like complicated generative modeling or so on. And it's actually been a huge success story, especially in computer vision in the last years. And this is kind of what I try to tap into here now, like to showing you what we have, what sort of impressive things we can do, but also where the current problems are. So AI and machine learning go well together. So AI is as Petra said earlier, a bit sort of like hard to define. But then one way to look at AI as a whole is to like ask that like can machines think? Can they be intelligent or so on? But then like machine learning then is kind of more practical, more like down to the earth way of looking at things. So more of like, can machines do what sort of we as thinking entities can do? And how does that sort of like contribute to photonics? Well, machine learning is kind of concerned with kind of adapting methods to observations or learning from past experience, or in computer vision especially, why machine learning or AI methods tend to work so much better than like traditional methods is that the AI methods kind of can interpret visual cues a bit similarly as we humans can. So like if you see a small person in a photo, we don't automatically assume that that person is tiny. We just think that, well, maybe that person is further away. And these types of like common sense. So machine learning methods are good at encoding common sense as regularizers in learning tasks. Yeah, that's how I would put it. And well, we can already do a lot of impressive things. And like if we look at like computer vision and machine perception, what kind of things have we been seeing in the previous years? Of course, like classifying things, like these small beasts that you carry in your pockets, like smartphones, or your cars have cameras and so on. As Jyrki pointed out earlier in his talk, that like the photonics are everywhere, data is collected everywhere, but also we have good methods to interpret that data. So complicated things like grasping style, art style, and going back and forth between like different art styles and generating, if not like excellent, but at least sort of like plausible alternatives representing styles of various art masters. This is something that came out a couple of years ago and was very impressive then, but things go forward with a like impressive speed. So yeah, this is kind of normal these days. So you're really sort of like taking a photo and then turning the photo into things that mimic art style from these masters. I think that's pretty amazing. We can also generate content like without actually like just from thin air. So this is impressive work from NVIDIA and Aalto University, where they actually have generated all these faces here are faces of people who do not exist. So a model that's been trained by showing like random images of like existing people, and then making the model sort of like grasp what it should do in order to mimic and be able to generate plausible high resolution photos of people that do not exist. And then what is like also cool in this piece of work is that you can also mix things. So like taking features from this person and then kind of combining them into a new person. So really sort of like exploring kind of the latent space of what's happening sort of in the face generation process. But there's more, like methods. It's a recent method in machine learning that can create images from text prompts. So here, for example, the prompt is that, well, an armchair in the shape of an avocado. And I'm pretty sure that such chairs do not really exist, or not that many at least. But the method has been trained on a lot of images, a lot of text. So then like the context of, well, a chair, an avocado, well, how can I mix these and so on. There's sort of like a lot of details here behind this, and it's still not perfect, but it can do impressive things. And I think that's the key, like impressive things. Not always very useful things, but at least impressive things. And I think this is certainly impressive. In computer vision, like of course, like scene understanding and perception is also quite crucial for, if you think of the future, if there's going to be self-driving cars and robots that walk around us in indoor spaces, they need to perceive the surroundings, understand what is a table, what's a computer, where the walls are, kind of these things that we humans do effortlessly, but requires quite a lot of work for AIs. But there's been great advances there. It's like how to classify things, how to interpret things, how to understand shapes of scenery, and so on. There's been a lot of like progress in that in recent years. And the same goes for like tracking and like perception for like movement, like doing that in real time. So you actually can deploy a robot or a car to drive the streets, understand the surroundings, where it are corresponding to previous observations and so on. So we can do impressive things, but that's not the end of the story. So AI is very much a field under research, and things are not perfect, or we aren't there yet. So even though we can do impressive things, there are a number of pitfalls, like snakes in the paradise, one could say. That's why there's a snake on the slide. These models are typically quite bloated and data hungry. They might require a lot of training instances. For example, like these models where you have face images, it's kind of easy to acquire training data. So that's kind of one reason why these models are kind of among the first to be solved. But then for many actual problems, for medical research or so, there isn't that much training data available. They are also typically quite hard to interpret. You will often want to know why the model reached a decision, what it did under the hood. This is not solved. And it's not always clear what the model is learning. Is it actually like sensitive to some very small details? Does it recognize a car based on door handles? Or like, because we cannot interpret the models, it's often a bit hard to say. Which brings us to problems with robustness and trustworthiness. This goes into the ethical domain. So if you can obscure like a traffic sign detector in a car by putting some like innocent stickers on the sign, that's kind of dangerous. And if we cannot interpret the models, how do we know that the model actually works when it's put it out in the real world? We cannot test with every possible input that it might encounter. So like the knowledge gathered by contemporary neural networks is sometimes criticized as spotty, pointillistic, well, useful, and certainly impressive, but quite often not very reliable. That's why we need FCAI and more research in these methods in the vision domain. We need to improve data efficiency. We need to make the things trustworthy and increase understandability. We still have 4 minutes for questions.
Thank you very much. It's extremely interesting presentation. Thank you very much. So now we have really time to the questions. So please use the chat box or just open your microphone and then make the question. So there is a comment, great insight into ML and current so on computer vision. So I would like to ask that I know that in Finland is extremely good in imaging. So there is a long heritage about the imaging. So how well Finland is in this topic using to AI in this imaging?
I would say like considering Finland is a small country, we are extremely strong in AI, and that's a good thing, of course. So we have both like a long history in like classical computer vision, but I think also the transition then like from like more classical things to a mix where people leverage the classical knowledge, but then also use these learning-based methods. That's been very successful. And we have good presence of top-level researchers in computer vision. Of course, we can always do better, but I think we are on a very good level. And also then like on the more like hardware side, I think there's a good representation of various researchers and throughout Finland in that sense. So I think this is also like well spread out. So it's not a Helsinki thing in any way, which I think is also important for Finland.
That's true. So this is interesting that now also not only the software but also the hardware. So they have a lot of common and there is even quite well clusters. So there is a questions. Would it be technically possible to completely mirror the real world in the VR? So you can see.
Yeah, I can see this chat here.
Yes,
that's a good question, I think, and there's also then like good people in Finland doing like graphics, and for Jaakko Lehtinen, whose work was the face generation here, he was involved in that project as the PI. So he has a background in graphics, and I think like VR and like making things like realistic is also very much like graphics related thing. And of course, really mirroring the real world is not not an easy task. But I think things are very impressive that can be done on that side. Really. I'm not an expert on that subfield, but I think there's already very impressive things.
So there is also other question. So can you see the chat box? So
yeah,
do you have a comment for that?
I think like unsupervised and like semi-supervised and sort of these like less supervised settings are certainly very sort of attracting and like the sort of research put into that. But my sort of like limited feeling from like industry experience so on is that they are not very much leveraged in actual application. It's still pretty much the traditional supervised setting in most tasks, and that's what I also see when supervising master thesis and so on for industry. So like I think unsupervised and semi-supervised things are still bubbling under in some sense. Yeah, that's just based on my limited experience.
Yeah, and then there is again more questions, so you can read from the chat box.
Yeah. Is data available a big challenge in doing AI research in Finland? If so, how do you cope with the challenge? This, of course, depends very much on what kind of applications you aim for. So typically, like if you develop methods, they can be applied to many different types of applications. And then, of course, you tend then to go to those where you have some data to apply your things to. But and then for like just developing methods, there's lots of like standardized benchmark data sets and so on. But then to actually solve like things in application domains, that's typically more like, for example, if we would collaborate with like medical doctors and medical researchers, then they typically struggle with the data availability problem. So it's often like then the application side, which then needs to face the scarce data problems on their part. And then, yeah, I think availability of data is often a problem in many sort of more applied like tasks and projects.
Yeah, wonderful. Thank you very much, Arno. It's very good presentation and extremely interesting. So there is a lot of common in AI and imaging and the hardware and so on. So thank you very much.
Thank you.
So we continue, and the next we are focusing about the AR and a little bit VR, need from AI to VR displays. And one and only Riku Rikkola, please take a floor.
Yes, here I am. Can you see and hear?
We can see you, but not your presentation yet. But we can see you.
Well, that's a good start. Okay.
Now we can see, and when you put in the presentation mode, okay, now perfect. Please go ahead.
Okay. So hello everybody, my name is Riku Rikkola. I'm with Dispelix OY, heading PD there, and talking today about AI and waveguide displays. It was actually not an easy task to figure out that how we specifically relate to the topic of AI. There are a multitude of applications. Most of the AR applications, I think, are somehow linked to AI, but I was trying to think that how actually we as a hardware provider and a component provider are related to today's topic. So briefly, to those who don't know what Dispelix does, so we are a relatively young company, 5-6 years old company, specialized in RGB full color waveguides for AR devices, such as glasses and headsets. And Dispelix specialty has been and still is that we do full color displays in a single layer. as others stack and do hamburgers, we do the beef. And we are the world leader in this field, and we also have big partners in order to go to market efficiently. And here you can see a couple of our partners, and also you can see our component there on the left-hand side. So it's a piece of glass with nano gratings on top, and one should use it like one would use an eyeglasses lens. So as said, there are many applications in AR for AI, and I don't start going through those, but I was trying to reflect the topic that how do we plan to apply maybe in the future the topic of AI in our developments. So I think that the first thing is waveguide design. We are using heavy computing power to design our waveguide displays and the gratings there. And we are using supercomputers to drive our algorithms and try to find the optimum solutions from performance and manufacturability point of view. And this has been the challenge of the whole field for many, many years. And we have this in-house tool that we have developed ourselves and continue to develop. So this topic of AI will be relevant in the future for our waveguide design for sure. Then other topic I would say, which is rather topical for us in this field, is metrology. We are ramping up the mass manufacturing of our components, and there we see, let's say, many challenges to overcome, but also opportunities to apply new methods. And these AI-based methods in quality inspection and control are something that we will surely apply and develop and apply in the future. And most obvious examples for this kind of activity are kind of the optical image quality inspection and also the visual component, visual surface quality inspection. Then I think that the biggest thing that how these AI developments, different applications, different end customer needs are reflected to us is really the quality of our component. So different customers, big and small, from different industries are looking for a specific, let's say, user interface and high quality see-through displays for their products and applications. And there are many specific things that are important for different customers from end user friendliness and usability point of view. And traditionally, one could think that the Google Glass and the earlier devices in this field, they are rather limited in every way. They do not have too much capabilities. Also, the image quality and the display quality is rather poor. So it doesn't create a much of a window to learn and view the wonders of the augmented reality and AI. And what we are trying to introduce to the market are waveguide displays, which are a new technology, but it offers a high quality window to any kind of data, any kind of images, any kind of representation of data. And this is what we are trying to achieve and do. And if you really look at these devices, let's say strongly connected to AI in different application areas, they are these AI headsets, and these three here are one of the most recent ones. And I would say that Magic Leap and HoloLens 2 are the ones with the best capabilities also. So what we are seeing is that there is a high quality display components inside, which we are doing as well, but not in these devices. There is a requirement for high field of view, which means that you can introduce digital content to a very broad area in your surroundings. And then many times in these devices, multiple focal planes are of interest. So you can present something very close to you and also a bit further away from you. And I think that there are some rumors that there might be in the future also devices where this AR and VR capabilities are combined, and of course the field of view is then huge. Then the other field of development is then AR glasses, and there we see that the Google Glass is not enough anymore. Well, it wasn't even at the start, but anyhow, also here, the target is for higher field of view. Many customers are talking about binocular fusion, which means combining the right and left eye images into one big image. And also 5G connectivity is something. So I think that these devices, which can be worn all day long, will be in the future devices, which are again used in many different applications of AI, and there are a multitude of those. So the summary really is, from our point of view, that these are the things that we are focusing on to serve our customers in a way that they have the best user experience in terms of AR and AI. So creating visibility is something which is important for our customers. Nobody wants to see the great things. They should be hidden inside the lens. One of the biggest challenges is waveguide efficiency, which influences the power budget of the device. If the waveguide is of low efficiency, you can actually not use the end device for a long period of time. And one of the most important things, and especially challenge in the field of diffractive optics, has been this color uniformity, and we have good solutions and offering here, but it always needs further development. And in order for the whole field to become mainstream, I think that the most important thing is really the form factor, which means that you would actually have a device that you would be happy to wear. So most of the devices today are not such. And finally, sorry, going back, there is still one picture of the thing which is important. So AI, different applications, and privacy is an important thing. So in many of the cases, one can see the image from the world side, and this is not wanted by the customers, as many of the applications are information sensitive and private. So the conclusion is what is happening here from our point of view, that there is a world full of AR and AI applications, and we are the window to that world. And what is happening is that our customers are creating devices which are already rather complex. They are even getting more complex, and they can sense their environment. There is wireless connectivity, and at the end, all this complex stuff will be inside a set of eyeglasses, but it will still take a few years. And hopefully at the time, DISPELIX waveguides are also inside. Thank you very much.
Thank you, Riku. Excellent presentation. So I think that we have time the questions. So they already said the same, that impressive work by DISPELIX. So I really agree that. So it's very impressive. But is there any the questions for Riku? So there is already okay. So there is a question. You can see that. How would you compare with Vario technologies?
I think that Vario is a virtual reality headset. They do not have this see-through displays that DISPELIX is developing. They are developing a complete end product, and it's a VR device. And what DISPELIX is doing is that we are developing these lens-like components, which will be inside and are inside AR devices. So the company products are pretty different, and Vario is focused on VR, and we are focused on AR.
Is there something, can you see something similarities? Of course, the AR and VR in different in that sense, but is there something similarities?
I think that many of the end applications are more or less similar. So we see we have same customer segments. So it's consumer, it's professional, sometimes it's government, it's training use, it's educational use. Maybe the big difference is that when these VR devices, many times you need to kind of, if not stay still, but you are not walking around, and those are not meant for all-day use. The holy grail of AR device is that there would be glasses like these here, and you could wear them like you would wear your own normal glasses, and they would provide you additional information which you find relevant and valuable. So I think that there are lots of similarities, but AR is going a bit further. And I think that there will be wider range of consumer opportunities and products, especially.
This is my special interest, of course, is that, okay, there is other question. So in which applications or domain do you expect the first big time breakthrough?
How we see the dynamics of the industry is that these US companies will drive the market creation. So all these big, let's say 5 companies that everybody knows, some of those companies are going to launch, and then the whole industry is going to follow. And we are already seeing some movement because Snapchat actually bought Dispelix's closest competitor, Wave Optics, just a couple of weeks ago, and at least Snap saw some value in Wave Optics.
That was the big news in that segment.
Was, we were happy to hear that, and interesting news, really.
Yes. And Facebook bought Oculus some years ago.
Yes, correct.
So my of course I forcing this Finnish high-tech technology, especially the photonics. So how well we are in Finland about this see-through technology, so that about AR technologies?
Of course, we have the best technology in the world. That's clear. But then I think that Microsoft presents a tough competitor and tough competition, and they also have activities in Finland. So really, it's great that we have this competence here, and it has been really, without the work done by different universities, especially Eastern University of Finland, so Dispelix would not have the employees we have today. So I think that still maybe more than 50% of our employees come from Joensuu area. And this whole cooperation in this photonics field is something really unique. So we are happy to be on board, and we are seeing great success by different companies. So we want to be just part of it and grow with you.
That sounds perfect. Then the last question related, how about Chinese market? Are you willing to commercialize in Asia as well?
Yes, so the plan is, I don't know how well that will then realize, but the plan is that then the big US guys will open the game, and then of course the Asian players will follow. And we have a presence in China. Actually, we are strengthening our presence there, and we are mainly dealing with companies who are in mobile phones business nowadays. So we are targeting the biggest ones and who have the capabilities. Also, then of course, Asia has lots of good ODM companies, and sometimes we also market our technology and products to ODMs who manufacture the products for the OEMs. So strong presence there as well. But I think that US will go first and Asia will follow.
Yeah, thank you. Thank you very much, Riku. Very excellent presentation. And afterwards, I think that we can share the presentation to the audience. Yes, thank you very much. We continue to our last presentation before we can discuss and make some conclusions. Is that solving the global food problem through the spaceborne hyperspectral imaging and AI. It's very interesting topic. So Jarkko Antila from Reactor Space Lab, please take the floor and give the presentation.
All right, thanks very much. Hope you can see me and hear me.
Yes,
see my presentation as well.
Yes.
All right, great. Thanks very much. Thanks for inviting. Been enjoying the event and being honored of being the last one in the group here. So I'm presenting a company that is actually working on space technology. So it's going to be maybe a little bit different point of view to the applications, but hopefully interesting. So we are still a small company, hopefully large in the future, about 5 years old. And we work on nanosatellites, different kinds of missions, space-based services. We are now we have created a new strategy and are in the middle of actually a funding round to get to this sort of new strategy and growth curve. So let's see what happens in the near future. But this presentation is actually about what is going to happen for us in the future. And if you don't know what's a nanosatellite, I always have one nearby. So this is a typical 2-liter nanosatellite. Looks like this. Nothing to do with nano except in the name. Okay. Short history about company. So everything started from the first Finnish satellite, Aalto-1, built in Aalto University, where the founders of Reactor Space Lab and also founders of ICE-I and many other new space representatives are coming from. The company was founded in 2016 by Reactor, the consultancy company, and the founders, hence the name. And 2018, the first satellite called Hello World was launched by us, and it's now flying a little bit less than 3 years, working well. And Aalto-1 already had a hyperspectral camera as the main payload. Reactor Hello World had the second generation of the hyperspectral camera as payload. And we've been working on other projects like these WQ Sunstorm, Apex, and so forth lately in the recent years, but now we are kind of going back to this hyperspectral and really want to kind of commercialize that. And we need a new version, and we work jointly with VTT to make those happen. And VTT has been the responsible of making those two first ones as well. So some pictures. So this is the Reactor Hello World on the left, and that's a couple of other kinds of nanosatellites. This top one just went out in mail to Central Europe a couple of weeks ago. This mid one is basically ready to be shipped any day. And then there's a little bit of longer term project that we are involved in, going to asteroid and taking hyperspectral images from that in the hope of finding something new to mine. But what we are actually now doing is that we are going towards our own constellation with the hyperspectral camera. So we've been doing satellites as kind of subcontractor work for others, but that's not hugely scalable. So what we want to do is we want to be the #1 global source for actionable green data. And what this really means is that when you look at the global ecological challenges that we have, you have the population rising, and by that you need about more than 50% more food. But at the same time, you already have used a lot of agricultural land, and you need to more like decrease it and increase the size of the agricultural area while decreasing climate emissions, while fighting all the kind of changes that are coming from global warming with drought, new diseases, new pests, and just the general adaptability of plants in the new era. And to do anything about it, we believe that you actually have to have first comprehensive global daily data on vegetation and soil. And that's what we want to provide. For those of you who are not familiar with hyperspectral imaging, very short version. So instead of a normal color picture, which basically has 3 color bands, hyperspectral image has typically tens or hundreds of spectral bands, often going above the wavelength or outside the visible range in spectrum as well. Especially when you go to near infrared, you start seeing these spectral fingerprints of materials. So you could basically analyze each pixel from with its content. What is it that it contains? And when you add the image dimension, you get, for example, concentration maps of certain substances. This mathematics involved is quite complex, and that's where the AI, or often in this case machine learning algorithms, come into play. I'll talk about that a little bit later. And I have to mention that in Finland, as we're kind of representing Photonics Finland also here, that Finland is very well positioned in hyperspectral imaging globally, with companies such as Specim and Zenop working here, and also VTT generating a lot of ground technology for that area. Typical application areas are precision agriculture, for example, fertilizer optimization, crop type mapping, things like that. But actually, currently, hyperspectral imaging is used in industrial applications as well, and for example, in food processing and recycling and things like that. And on the right, there's an example picture from Hello World with some analysis on different types of fields. So that is the satellite that we now have up and running. So how we will, in practice, do this daily operation, we will ship out a constellation of small hyperspectral satellites. We will have enough of them to provide daily data, but the performance will be comparable to previous larger scientific satellites through the specific technology that we have available here in Finland. So we will have those miniature hyperspectral images providing 20-meter ground resolution. And then we will combine this with advanced AI machine learning methods and kind of a data service platform. And we believe that by this, we will significantly help in fighting this sort of ecological crisis. For example, there's a study saying that if 16 major crops would be providing 95% of their full potential, then global production output would be increased by 58%, which would already solve the food problem. So that is kind of what we are aiming at. And globally, we can do a big difference in increasing yields and decreasing costs and decreasing environmental impacts. And the big impact is actually coming from the cost in addition to the performance. So compared to somebody ordering a drone campaign to their fields every single day throughout the year, or getting the service from our space-based data, we are about 1,000 times lower in cost in providing that data. Of course, drones can detect like a centimeter level differences if there's applications for that, but fertilizer need, biomass estimation, soil organic carbon, things like that don't need that. So where do you actually need AI? And I have AI in quotes because it's it's a strange term sometimes. We're mostly looking at machine learning at this time, at this state. So basically, creating algorithms that can provide crop maps, for example. It could give you a map about watering needs or a map about fertilizer needs, and instructions on what to do at the end, so that it becomes very valuable for like farmers in this case. But the problem is that there are huge amount of variables along the way. First of all, you have a lot of data. You know, if you don't know what's happening after Terra in the multiple orders, then you have to go look it up, and that's what we are talking about. Then we have multiple instruments flying out, and anybody has done any spectroscopy knows that the device-to-device variability needs to be handled. Atmospheric effects, you know, what are the cloudiness, what's the moisture, all that kind of stuff. Weather in general, where does the light come from, the lighting angles, perspective. Are you seeing, you know, that crop from an angle or straight or something else? Plants are evolving over time. You made a calibration last year. Does it hold this year? Crop and soil cross effects. Okay, you see, you know, 10% of soil, and in another field, 20% of soil. So how do you actually compensate for this? And then phenotyping is also, like, at which phase is the growth, and you cannot solve this equation as such. So what you have to do is that you of course have to by design the constellation of the camera to minimize all these effects. But at the end you have to train the algorithm. So you have to generate a kind of a global network of data gathering machine that feeds into this machine learning pipeline, and you need to automate it so that it continuously improves and adds different applications, because then, you know, these same problems can be different for the different applications. So it is really to handle the complexity and the evolving biology of the globe that is kind of why it is mandatory for us to do machine learning. And then at the end we get, for example, in agriculture, these kinds of services. We can offer advanced crop nutrition, precision watering, seed selection, planting and harvest, early warning, protection against fires and pests. And these have different values to different kinds of customers. So it's a big sort of portfolio to handle, but that's where we are definitely going, and are seeing that we have the tools to disrupt this scene. So that was all from me. Thanks very much. Any questions?
Thank you very much, Jarkko. I think we have now time to questions. So there is already, can you see the comments chat box? So there is a comment about the food, and then also comment about the presentation. So can you see it?
Other ways to tackle the increased food demand is to decrease food losses of production. I guess that's a comment. Yeah, there's certainly, this is not the only way to improve the yield while kind of handling not contributing to the negatively to the climate change is one part of the equation, but it's more complex than that.
Yes. Do we have other questions to? Okay, there is. Please read the question and give a comment of that.
Okay, so who are your customers? What kind of business model? So we have are going to have for this several types of customers. It's mostly business to business, business to government type of business in the beginning. So reaching like end farmers directly is a kind of a tedious job, but there's lots of large companies managing a huge amount of agricultural fields, or industrial companies, managing industrial sites where they want to detect also like natural gas leaks and things like that. So there are applications outside agriculture area. And our business model is service business. So we provide, depending a little bit on the customer, data, or then in a way the sort of the end result instruction maps, and they are at different prices, but the business model is subscription, monthly subscription.
Any other questions? So I think that we can continue about that kind of question and answer topic, so that if our all person who gave presentations who are still here, I know that couple of person need to leave, but if there is Jyrki or Petri, Janne, Irina, Arno, Riku, so if you can open your video, so there is a possible to give questions. So we had a great event. So there is the last question for Jarkko, so that how big the business is, and then we continue to the common questions.
Well, it is rather big. If I'm not sure if I dare to give any exact numbers, but we're talking about hundreds of millions.
Yeah. So it's quite huge. So also I would like to ask to Heikki Ailisto if you can also open the video and say something, because this is the common force with photonics and artificial intelligence, and basically together with Heikki we are organizing this. So thank you very much, Heikki. So if you would like to say something in this phase, so please go ahead.
Yeah, thanks for all the presenters for great and interesting presentations. From old times, I have background from computer vision, machine vision, and now I'm more working on the AI side in similar role as you are here. And I have to say that I learned a lot during today, even though I should be an expert on the both areas, but lots of new things. Great presentations.
Yeah. So in basically, I have that question for our the presenters, that did you learn something today? There is something what you learned about this event. So who would like to start? So it may be the Petri, if you would like to start. So you was the first speaker.
Yes, obviously I learned a lot. Actually, I have a question to Jarkko. We have had some attempts to kind of replace hardware with clever AI software, and you may know, for example, there was an attempt to Spexel. It was the kind of a startup idea. Do you think this approach is feasible, and how far can you go? I mean, it would, regarding, for example, satellites, it would save a lot of space, I believe. But are you exploring this path?
Well, partly, I guess I could say that there are some thoughts about those kinds of approaches, but I think that looking at our applications, there are so many variables that the more you can fix with good hardware, the better, the easier will the end application to actually be realized in real life. So I don't say it is impossible, but it's most likely going to be needing even more training data to get the applications working. So it's kind of a trade-off. It's difficult to say, before really testing it, that how well it works. But in general, I think I agree that if you gather the the photons somehow that tells you about whatever you need to know, then there will be a method to analyze it at the end. But yeah, the more variables, the more time it takes.
Yeah. How about Irina? Did you learn something? So is something new about the AI environment in Finland?
Yes, I learned a lot. It was very interesting to find that its neighboring country like Finland, small one, they are so advanced research in artificial intelligence. And I would like to have maybe some projects with Finland.
Oh,
because I have big experience in lens design, more than 40 years in lens design business and research. And so I hope we can do something together.
Oh, that's the continue, because the next question is that do you have already something idea that what we can collaborate between the photonics and AI, and maybe the Irina, if you would like to continue, because this is obviously
you can do in all these three directions. And I already discussed with Jyrki Saarinen, Professor Saarinen. Maybe it works because the expert system has to be pushed and it will work. Then computer-aided design also, some ideas, just take it and start doing. And then databases is a general project for which is good for all over the world, for lens design all over the world. So it is all interesting and booming areas now. So we just take photonics and use artificial intelligence, and it will be new direction. And that when I presented it in Taiwan seminar online, this is Taiwan conference on the optical design and fabrication, they asked me a question. Is it some prediction that optical design specialty will be still used in future, or artificial intelligence will kill optical designer? My reply was it will be optical designer will stay forever, and artificial intelligence will be help of it in routine, mostly in routine procedures. But when it can feel, then we can tell that it is will kill lens designer when it can feel. But till this, it is not possible. It will stay. And it was a question from Japanese professor, and he says that he is very glad to hear that lens design will stay for future.
Yes, so Jarkko needs to leave. I think that there is some other meetings continue. Do you want to say something? There is some question there for you. So first a good presentation, and then there is some how big fleet of satellites you will need for accurate and frequently enough coverage of the whole globe.
All right, yeah. So we believe that with 15 satellites, we'll be already providing good commercial service. With 30 satellites, we are able to provide data or even more frequent data on the land area, which is equivalent to about the size of Europe or a little bit bigger. So we're talking about some tens of satellites, depending on a little bit how we optimize the orbits. But thanks very much. I need to go and start our annual general meeting actually in about 5 minutes. So
okay, thank you very much.
Papers.
Thank you very much.
Thanks.
Bye-bye.
Thanks a lot. Bye-bye.
So how about Riku? What kind of final words you would like to say about AI and photonics and that kind of possibilities?
Yes, unfortunately, I was not present in the early part of the meeting, so I do not have any questions. I would only have one. So how come you are so fast in the construction in Joensuu? Because the Photonics Center seems to be ready.
Yeah, it's already. It is the virtual work, so it's
okay.
much faster than concrete.
Okay, so really, I think that we have huge opportunities, everybody here, and at research level, the good work should continue, and even the volume should increase, and also in business. So we need brave entrepreneurs who want to conquer the world in a way that not to be satisfied for something small, but go for big, and that's what we can do, I think.
Yes, thank you very much. So, Heikki, do you want to say something about the end of this event?
I think that we had a lot of kind of cues or leads where AI and photonics could join forces. For example, what Irina said, what the company presentations told, that and Apasi gave examples how it's already done. So there's huge opportunity for this kind of joining forces for common good. So very good in that sense. We just have to now kind of prioritize where to start.
Yes, that is very easy to agree that there is a lot of potential, lot of leads, lot of that kind of ideas what we can continue. So this, I think that this event proposed is that we somehow learn from each other what is possible, what kind of situation we are. So I think that this event was the perfect for that, and gives us a lot of good possibility to continue our common work. So I think that now it's time to thank you very much. Have a wonderful rest of day. Sun is shining, at least here in east part of Finland, so probably whole Finland. So thank you very much and goodbye, and this is a good starting point. Thank you very much.
Thank you.
Bye-bye.
Bye.
Bye-bye.